Hey guys, today we're going to look at kinematics equations. These are equations that you're going to be able to use in more complex situations or if different variables are given to you than the normal ones that we've already seen. Hopefully this will be a quick slideshow. It's just a breakdown of the equations. So here are the variables that you need to know. Final velocity, which is VF, we've already seen that one. Initial velocity, which is VI. Acceleration, final position, which is XF, and initial position, which is xi, and then time. These are all variables that we've used in the past. We're just going to rearrange them in different forms of the same equation. Okay? Now this we can replace with change in velocity at any point in time, and this we can replace with change in position at any point in time. So instead of xf minus xi, we can put a delta x in the equation. So our basic formula of velocity, I left a lot of space on this slide because it's a lot of mathematics and rearranging equations. We have v equals xf minus xi over t. Now this equation is one that we're going to use quite often, but we are also going to possibly solve for the final position instead. So instead of using the equation in this way, in this form up top, we are going to rearrange it to solve for the xf to keep that by itself. So underneath, I'm going to start the rearranging. So in order to isolate xf, or the final position, we need to get rid of this t from the denominator. So we're going to multiply both sides by t. And these two cancel out, and that leaves us with v times t equals xf minus xi. Now, we're not done yet because xf is not completely isolated. So in order to get it by itself, we have to add xi to both sides in order for those to cancel. So I'm going to rewrite our final position down at the bottom. xf equals xi plus v times t. Okay, so this is an equation that we can use to solve for the final position. It is just a mathematical rearrangement of the velocity equation. Now we're going to look at our acceleration equation. We're going to do the same thing. A equals VF minus VI divided by t. Mathematically the same exact equation as the previous slide. The variables are different, but the math is the same. So if we're going to solve for the final velocity, we're going to go through the same steps. Multiply both sides by t to cancel these out, and then we have AT equals VF minus VI, and we still want to isolate VF, so we're going to add VI to both sides, and our final velocity equation is VI plus A times t. Now, this is going to be an often used equation for us. I'm a lot of times going to say if your initial velocity is 10 meters per second and you accelerate at a rate of 3 meters per second for 5 seconds, what is your final velocity? And you can use this bottom equation so you don't have to mathematically rearrange anything. So far you should have 4 equations in your notes or on the sheet of paper for you to reference. The original velocity equation, rearranging for final position, the original acceleration equation, and rearranging for final velocity. All of those should be in your notes. Now we have a lot of longer equations also. More often we get pieces of information in a problem and not the final calculation. So a lot of times I will give you the initial position and the final position, but not the actual velocity, because those are interchangeable in some of these equations. So these equations down at the bottom are other options that we can use to calculate the same information. So we have final position equation equals initial position plus 1/2 VI plus VF times t. Another version of the same equation is the final position equals initial position plus VIT plus 1/2 AT squared. And remember, only this t gets squared. The 1/2 goes to the a and the t squared, but only the time gets that squared value. And then the final one, which is VF squared equals VI squared plus 2a delta x, or xf minus xi. Now these 3 equations you have to pay attention to. This first one can solve for any of those variables that are listed in that equation. We use this one if we were not given the value of acceleration, because notice acceleration is not present. The second one It gives us everything except for final velocity. So you cannot use this equation if you're trying to solve for final velocity because it is not present in the actual mathematical equation. You can solve for anything that's listed here when you rearrange to calculate. Now this last equation is a special one. It does not have time in it anywhere. So if I do not give you time in the problem, this is likely going to be the equation that you're going to go with unless it's asking you to solve for time. Because remember, if it's not in the equation, you cannot solve for it. So this bottom equation, you can solve for VF, you can solve for VI, you can solve for A, or you can solve for either of the positions, but you cannot solve for the time. So we're going to look at a couple examples. Example 1, find the displacement of the plane that experiences uniform acceleration from 66 meters per second to 88 meters per second in 12 seconds. So we want to find displacement. And notice it gives us two velocities, but not an acceleration. So we're actually going to use this first equation right here. Okay? It gives us two velocities, but no acceleration. So we have to use this equation. I'm going to write it down. xf equals xi plus 1/2 vi plus vf times t. Okay, so the plane experiences uniform acceleration. Since it does not indicate our initial position, we can assume that our initial position is 0. So we can cross that out and rewrite the rest of the equation. We have VI, we have VF, and we have T. So the final position is 1/2 times 66 plus 88 times 12. And once we go through and calculate all of that information, we can find out that the final position of this plane is 924 meters. We know that we measured in meters per second for this information, so our final answer has to have meters as our distance unit. So example number 2, a car has an initial velocity of 10.5 meters per second. It will accelerate at negative 0.4 meters per second squared over a distance of 75 meters. What is the final velocity of the car? So notice we have a velocity, an acceleration, a distance, but we do not have time. So we actually have to use that VF squared equation. So VF squared equals VI squared plus 2A delta X. Okay, VF squared is our unknown, or VF is our unknown. VI is 10.5, and we're squaring that, plus 2 times negative 0.4 times 75. So I'm going to do these calculations separately. 10.5 squared is 110.25. And 2 times negative 0.4 times 75 is negative 60. So we're going to combine those two numbers to have a value of 50.25. And then our last step, since we want just the final velocity, we need to square root to get rid of that squared. And it ran out of space, so the final velocity is 7.08 meters per second. And again, we know it's meters per second because up here we have meters per second, meters, and meters per second squared, so those all end up canceling out. Okay, so when you get into class, this is what we're going to be working with the next few days. There are going to be a lot of examples and a lot of practice problems because this is a large portion of what we're going to build off of in future units. So we already had a few kinematics equations from previous sections, and we're adding on to some of them here. So now you should have a total of 7 or 8 equations from all of the sections of notes from this unit.